Okay, I'm Jian Zhao from University of Notre Dame, and I'm currently a PhD student at Mila UDEM. Today, I'm going to give a talk about our recent work, self-supervised graph structure refinement for graph neural network. Okay, so let me first introduce the background and motivation of our work. So as we all know, there are several limitations of the current graph neural network domain. And most GNNs actually perform message passing on the raw graph structure. However, this raw graph structure is actually could be wrong, and sometimes it is incomplete, and sometimes it is noisy. So there is a current type of works that solve this problem by graph structure learning, which learns a new graph structure instead of relying on the raw graph structure. So the goal is to jointly optimize the graph structure and also the downstream task. So here is a general framework of the graph structure learning. Given an observed graph structure, potentially also with some features, we perform a structure modeling and obtain a new refined graph structure with some edges modified. And then we have some, we can have a GNN or some other methods to obtain a node embedding and optimize the model by the learning objective. So how can we get the adjacency metrics in this structure modeling step? There are several ways. One is to use the direct parameterization of the adjacency metrics. However, I think this method is not quite commonly used now because the cost of modeling all the parameters of n square complexity is really high. And the second is a probabilistic approach, and the graph structures are sampled from the distribution generated from the learnable parameters. And the third is, I think the current main trend of graph structure learning is to use a metric learning-based method. Basically, we want to calculate the similarity between the potential edge node pairs. And then based on that similarity, we can perform KNN or epsilon NN so that we can generate the new graph structure. So there is also a survey. If you are interested, you can follow that. So as I have introduced before, the graph structure learning performs. I think performs one important step is the graph structure estimation, and then performs GNN on downstream task and optimize the graph structure and the GNN together, so that these works can be categorized as the joint learning of the graph structure and also the GNN parameters for exactly the downstream task. However, this type of learning is erroneous because the first problem is that the inconsistency between the graph structure learning and the application. So as we all know, the application could be many. There are graph level and node level tasks and edge level tasks. So however, in the real world cases, these tasks may not be aligned with the graph structure learning. And also what makes things worse is that most potential edges are weakly supervised. So that for example, in semi-supervised node classification, we are basically overfitting the graph learning structure learning part for sparse labels. And this is also argued in this paper. So that this graph learning process is demonstrated to be inferior of our strategy in the experiment. And the second limitation is that there are, as we all know, there are abundant unlabeled data in graphs. However, fitting only the graph structure only on the labeled field label nodes could be less usage of this abundant unlabeled information. And the third is the scalability problem. Since we are both modeling the graph structure learning and the model together, this could be time and space consuming. so that we cannot directly apply these methods to large graph applications. So in light of these limitations, we propose our solution in a pre-training and fine-tuning framework. Basically, in the pre-training phase, we want to fully estimate the potential graph structure by a self-supervised link prediction pre-training task. Then, after perform the pre-training task, we can successfully estimate the graph structure in the fine-tuning phase. So in the fine-tuning phase, we boost the GNN learning in two ways. One is to initialize the fine-tuning GNN by a pre-trained GNN, so that the knowledge of self-supervised learning could be easily transferred. And the second, we optimize for downstream application based on the refined graph structure, so that we can alleviate the incompleteness and also the noise problem. There are also some benefits. The first is that since we are separate the graph structure learning part and also and the GNN training part, we are actually achieving much more appealing scalability. And the second is the utilization of rich unlabeled information in the graph. And the third is the scalability. And there are also some challenges since we are performing graph structure learning without using the supervision. So it is a much more difficult task. And the second challenge is that the graph structure learning basically assumes that the structure observed is actually inferior, which is incomplete and noisy. So to solve these challenges, we propose our method. So as I've introduced before, given a GCD matrix and also the structure and the node features embeddings, we can use the self-supervised graph training, graph structure learning to pre-train a link prediction task. So after the pre-training step is done, we can initialize the fine-tuned GNN by the pre-trained GNN, and also we can refine the GCD matrix to perform the downstream task. So let me go through the details of the pre-training model. So in the pre-training model, we actually performing link prediction. So we follow MoCo to develop a self-supervised learning contrastive learning framework. So basically, as we are utilizing the different modality, namely the structure and the feature of the graph, we are actually performing the multi-view contrastive learning here. So the first type of multi-view contrastive learning is the intro-view contrastive learning. Basically, given a node pair, given a batch, we perform subgraph sampling for all the nodes in a batch, and then we get their feature and the structure embedding. So the structure embedding could be some structure related, such as deep work embedding, or some feature and structure related, such as GNN embedding. So basically, there are two views: the feature and the structure view. And then we perform the intra-contrastive loss. Basically, we want to predict whether two nodes are correlated and perform. So this is a link prediction task. And if they have link, they should be far more similar than the other node pairs inside the batch. So optimizing this MoCo, this SSL loss, we could achieve intra-contrast. Basically, that is the link prediction based on the feature only or the structure only. So there is also an interview contrastive learning designed in the model. So in this way, we want to capture the correlation between cross modalities, namely the feature and the structure. So the idea is to let both modalities be the key query and the key encoder, and after the embedding is encoded by another cross modality encoder, we could predict whether they are similar by the SSL loss. So after after obtaining the interview contrastive learning loss for a given batch, we can optimize both their intra-contrastive loss and also their inter-contrastive loss balanced by a coefficient alpha, which is a hyperparameter. So once we obtain the loss, we can perform pre-training. So in pre-training, we care about using feature and structure to predict the link by themselves or by the cross modalities. So after the pre-training is done, we want to migrate our pre-trained knowledge to the fine-tuning phase. So there are two types of migration. The first is the migration of the pre-trained knowledge. Basically, we want to initialize the fine-tuning GNN with the pre-trained GNN. And then we want to refine the graph structure, as the original graph structure could be erroneous, so that we add several non-existing edges and remove existing edges. So this process is also done by a unsupervised metric learning. So basically, we tune the hyperparameters to balance different type of graphs and generated by the cosine similarity matrix. So the intuition is that we can, after we have trained the GNN to perform link prediction, we can perform link prediction on both modalities, which is we can generate feature similarity graph and structure similarity graph, and then we can filter them by some ranking methods, and then we can fuse them to a single graph by a hyperparameter beta. And finally, is the optimization of the fine-tuning GNN. So basically, this is the same as the previous, such as node classification or link prediction task. So let's see how our methods work. We perform our experiments on several datasets, including a very large OGB dataset, and there are several baselines included for GNNs and also for JSL works. We can clearly see that our methods achieve far more better performance, and also we can see that our method is quite scalable. As for traditional graph structure learning methods, they experience out of memory issues on OGB archives, and we are able to perform. Our method is also very fast. We can perform OGB archive training in 3 minutes. And as I have introduced before, directly tuning graph structure on a few label data could be erroneous, especially when the label rate is small. As we can see that with different label rate, our proposed framework GSR consistently outperform other methods. And especially for set-theory, we can see that at the label rate of 1%, our method achieve far better performance than others. And there is also a efficiency and the scalability advantage of our method. On Cora, we can achieve 13 times faster with much less GPU memory. And the same is also true for other data sets, and we are able to train OGB data on a single GPU within 3 minutes. So there are also some interesting conclusions found on several data sets. We can find that for Cora set-theory and OGB archive, which are both citation networks, we can see that adding and removing edge in this type of method, namely how we refine the citation graphs, are quite similar. We can see that basically we want to remove the edges in the Cora set-theory and OGB archive as the basically we want to add the edges. Basically we want to add the edges on these graphs, since the links in the citation graphs are quite high quality, and we don't want to remove them. and we have some other different conclusions on several other data sets. So as we have introduced, there are several hyperparameters to tune. The first is the alpha parameter, which balance the intro and inter multi-view contrastive learning. As we can see for all the data sets, we have to balance the intro and the inter weight so that we can achieve a better performance, and only perform one type of contrastive learning is leading to inferior results.